Hello, I'm Jeffrey Fox in the Big Data Open Source Software and Projects course. And here we're going through the unit, which is Big Data Applications and Generalizing their Structure. And it's Lesson C, where we move on to streaming applications in the Internet of Things. The earlier lessons largely focused on images. So this is where we are, Internet of Things, but also other streaming problems. So here we have some general remarks about the Internet of Things and streaming. We only do a sample of streaming because actually the majority of the 51 use cases did streaming, partly because experimental science always gathers data in the stream. Most commercial applications gather data in the stream because people are sitting there searching independently and streaming their searches into the engines and things like that. And then, as I said, some of this streaming is batched, as we saw, for instance, in the last lesson where we looked at the Croesus data, which backed everything in a 1 to 2 month field trip. Well, we all know that there's a lot of streaming, a lot of Internet of Things, and there's estimates by 2020 there'll either be 24 or 50. Probably these estimates are not as far apart as you think. They're just making a slightly different definition as to what an independent device is, because often devices are grouped together. And you might count some multi-component devices, 1 or 2 or 3 devices. So as far as I know, there is only one reasonable thing to do, which is to use the cloud to control these devices. And it's the source provider for the Internet of Things. We also have this other important aspect. We saw that when you have your sensors sprinkled around, you might have local computing. We saw that for the telescope, that was particularly natural because it's perfectly reasonable to put a decent computer next to a telescope. It's not so reasonable to do that for your drone buzzing over some buzzing over some battle or something in the front line, or a tank or something like that. They won't have really, they're not going to use up space with computing. So this covers areas like smartphones. Actually, as I say this, Apple just announced its watch for next year, smartwatch. So this is all part of the tremendous revolution expected. This has been forecast for some time. I remember smart homes were a big thing just before, in the late 1900s. And I actually bought books on it just because I thought of equipping my home with all sorts of nifty smart devices. I actually decided, probably correctly, that it was too early to do that. Anyway, you have concepts like ubiquitous cities where everything is smartly linked together. Robotics, where the robot is incredibly intelligent, partly because it uses the cloud. The simplest example of that is possibly the self-driving cars, which obviously do a lot of their decision-making locally, but they use the back end to provide key information, such as the latest maps and everything like that. So here we have some sample that we've identified as just being exemplar of the Internet of Things and streaming apps. We have the cargo shipping use case 10. We've already gone through this case here of the streaming data from defense applications. We have the sorry about that. We have an example where it's the streaming comes from people, which is Twitter data. Here we have the streaming coming from an instrument, the CERN accelerator, describing the Higgs particle event by event. Each event is streamed, if you like, independently from the collision where the proton and the antiproton crash together, and here we have actual more classic environmental science where data is streamed from environmental sensors. And then another important example of sensors is power grids, where hopefully we're going to get better use of electrical power by equipping every part of the power grid with intelligent sensors. Here is one of the plots of the trend in sensors. These are the electromechanical systems, including on devices such as phones, laptops, cameras, etc. And the dominant one is actually, of course, phones here, followed by tablets. It's well known that actually, if you want to try to do work in the sense area, the best, most widely deployed sensor is the smartphone. And here we have, by 2013, 8 billion such devices. So that's quite a lot. Actually, about one per person. Here we have a slightly cruder classification, smartphones again, PCs, tablets. Here we have the true Internet of Things. This was done around the end of 2013, but extrapolates to 2018 and gets to the 18 billion mark. So this actually, if you look at these numbers here, these are more consistent with the 20 billion devices in the Internet of Things by 2020. They're not really consistent with the 50 billion number. Here are some examples of why smartphones are important. Here we have the 27 version of the iPhone with 3 sensors. The iPhone 5S, of course, we just got the iPhone 6 a couple of days ago, and it has 5 sensors. Here we have the equivalent thing for the Android lines from Samsung with the Galaxy S5 and with 10 sensors. So I imagine the iPhone 6 is similar to the Galaxy. We know that the critical new sensor in the iPhone 6, which is actually present in a lot of Android devices as well, is this NFC sensor to be able to do very convenient payment using your smartphone as essentially a generalized credit card. Here's the same picture we saw before, just reminding us again that those things correspond to this thing here. So this picture here is illustrating this from another point of view. We have here all these sources of sensors. Here we have some sort of water pouring being measured. Here we have actually an array of seismic sensors. Here we have your smartphone. I think this is probably already a telescope, satellite, and here we have a webcam, a telescope, just data sitting in a database. Here we have the Large Hadron Collider, another satellite, and so on. So here we have sources of data. They're either instruments, computers, or data sets. Possibly the thing like a Croesus is flying on an aircraft. These are pouring data into an ecosystem. That ecosystem I used to think of as a grid, but now I think of as a cloud. And that cloud consists of filters. Those filters are typically controlled by Storm. If we do it in Apache architecture, these things here are publish, subscribe. In Apache would be publish, subscribe edge points. Then we initially process with Storm, and then we would have nifty artificial intelligence. Remember when we did the defense? The last part of the defense thing was the conversion of knowledge to wisdom and decisions. That's what I sort of mean by discovery cloud. Make that final decision as to whether those objects we'd identified were enemy vehicles or whether they were particularly dangerous and so on. So that's the final intelligence decision. And then here we have our analysts or warfighters or what have you sitting there making decisions. This is a very nice, I like this diagram because it describes this pipeline. And you can have as I pointed out, there's a gray area as to what you put in which step in the pipeline. But the main thing is the pipeline goes from raw bits and bytes to critical decisions like let's declare war, or whatever we're trying to do. So here we have an example of actually what I'm doing in my research group with my graduate student Supon. And here we have the device goes to the pub subsystem, which is either in our case Kafka or RabbitMQ or ActiveMQ. Then it goes to Apache Storm, it goes to data stores, and it goes to data analysis. And we can see here how the pub subsystems are arranged hierarchically. It's all coordinated by Zookeeper to make certain we keep these distributed systems consistent. We store everything in some sort of NoSQL system, HBase, and we process it with Hadoop, Spark, Twister, what have you. And here we have, I say, all these devices sitting here. We illustrate here with this TotalBot, which has a Microsoft Connect added to it. Here are some examples of Storm performance. This is very preliminary data, which we're redoing, and we're using this for drones and Connects. And here's some plot of the response time, and it gradually rises as effectively the amount of data to be processed increases, and you'll find that it actually does sort of, well, not quite that, does this. Namely, at some stage, the amount of data entering the system exceeds the size of the system, so it cannot keep up. When it can't keep up, the system essentially is hopeless. It basically has infinite response time. So what you do then is you use the fact that the cloud is elastic, and you go from one broken machine to lots of broken machines, remembering that Storm can coordinate lots of brokers using Zookeeper to keep track of what's going on. So that's a huge advantage of the cloud. It's elastic. This allows you to actually deal with a world with 8 billion MEMS devices, which are moving around and coming online and offline and things like that. That makes it all work. So here we have the cargo shipping use case 10. This is, if you like, the FedEx, UPS, DHL use case. USPS maybe. This is entering the same type of market. And we have data is going from this streaming through the system. Here we have data moving around. It's going from one warehouse, jumping on a ship, going to another warehouse, and so on. And everything is tracked with various standards, labeling for recording what it is and where it is. And in principle, all this movement of entities, whether they be your Christmas pudding being shipped from Amazon, or your new car, they're all can be tracked automatically, and so you can in real time find out what's going on. So this is a classic example where obviously a lot of work's been done already, because obviously UPS, FedEx, etc. use such tracking, and you can actually pretty usefully go online. You don't get continuous tracking, you get discrete tracking from various stopping points. Here we have an example of environmental science. So, when you discuss sensors for science, you think of sensors attached to polar bears, to squirrels. Another type of sensors are like those which are used to do GPS measurements for earthquakes, which are permanently located on some big physical things. Here we have an actual pretty big sensors, and they're just observing various aspects of the world, whether they be the movement of this. But these ones are observing effectively what the atmosphere is made up of, so we can obviously track pollutants and other things in an effective fashion. As I say, we don't have 20 billion of these, we just have 500. And that's why I said that when you look at sensors, if you want to get the large numbers, you really have to go to smartphones. If you go to today to current sensors, you do get a few more, we'll see, for the energy case. But for a lot of other problems, although there's potentially huge numbers of sensors, at the moment there are not that many. Because then you wouldn't have that many of this type of sensor, which are pretty big. So obviously there are big sensors and little sensors. In fact, the biggest sensor of all is the Large Hadron Collider. It's just one of those, and it just pours 100 petabytes of data at the world over a few years. Here's the example I mentioned of the smart grid. And this comes from work at the University of Southern California, where we have 4 terabytes of data a year for Los Angeles. And here we actually, I say, we have more sensors, 1.4 million. This is another field which is using MATLAB. Wake is a well-known open source sort of machine learning library, and of course Hadoop is used to integrate everything together. There's a significant privacy issues, because obviously if you know who's using energy, you're knowing something about a person, and that's sort of sensitive. So you have to be a little careful how this data is used. And but there's little doubt that such sensors, smart meters, are very important. Notice these are not. We have different granularities. Video is 30 times a second. This one is once every 15 minutes. And people tweet, probably people think in the time scale of, like in the video time scale. People think at a few times a second, so they're going to be tweeting with time scales of seconds. So all of these streaming applications have different time scales attached to them. But here, of course, the goal is to have the wide-scale deployment of these smart grids, which will allow us to use energy much more effectively, which is well known to be a very important thing to do. Here is an example of another form of sensor. The person is a person tweeting. Obviously, tweets are a very good example of sensor data. I think actually in this particular Truthy project, they do not look at the microsecond, second by second use of Twitter by users, although in principle you can, and some people actually use Storm and PubSub to do that. Rather, they gather the data in batch fashion from Twitter. And this gives you, again, what for these users is a large amount of data, 30 terabytes a year after compression, and 100 million messages per day. And you want to do near real time. So it's not actually real time. You batch the data. I do not know exactly what the batch time is. This particular group is using HBase, an extension of HBase, to be able to do the customized indexing needed for Twitter data, which has time and spatial tagging, and it uses HDFS for the basic storage. It used to use other NoSQL systems, Redis, but that's an in-memory database. But they actually switched to using a more straightforward HBase backend NoSQL system. This is, of course, work rapidly changing, because at least in the academic field, this type of study is relatively new. And again, you're sort of like astronomy. We're looking for anomalies, exploding stars and things. Here we're looking for, we're trying to understand communities. We're looking for anomalies like, Twitter's well known to be one of the best ways of finding out about earthquakes, because people tweet about earthquakes immediately, or storms, or tornadoes. That information comes almost immediately from Twitter, whereas you might have to wait longer time for the instruments owned by the government to tell you what's going on. Here we have, I say, the largest source of streaming data, which is the CERN Large Hadron Collider, 27 kilometers around circumference, all around here. And then we had these various experiments: Alice, Atlas, CMS, and LHCb, the 4 big experiments. Those each gather data. They have huge. If you go to one of my MOOCs of my applications class and analytics applications class, it goes through this physics application in detail and has nice pictures of all the apparatus, which is huge, much bigger than, there's a picture of the apparatus and people, and you can see that the apparatus is several times taller than a person, and across is huge. So, and another important thing is each of those 4 experiments has lots of participants. CMS, which is one of the larger ones, CMS and Atlas are the largest. That has 3,600 participants, 183 institutions in 38 countries. And this data is spread around the world for its analysis. And that's shown here. This is the multi-tiered analysis for all the LHC experiments. They are implemented differently, but the basic idea is the same. You start off with your single source. So this is sort of interesting. You have different types of sensors. With a smartphone, you have billions of very lightweight devices pouring out data. For LHC, you have one device, a very expensive, hugely powerful device, which is a single sensor or instrument is pouring out the data, and is pouring out data continuously at this rate here of 200 to 1500 megabytes per second. That data is then strewn around the world. Some of it stays at CERN, I think about 20 to 30%, and the rest is sent around to so-called tier 1 centers, which are 1 per country or 1 or 2 per country. And then they go to tier 2 centers, which are typically at universities, maybe 50 to 100 universities per experiment. And then finally it goes down to the local research group, which is the tier 3. That's where you actually do the discovery. And this data goes through various steps. Raw data to process data, which does not change the size dramatically. Then you go to much more compact data forms, and those compact data forms, which just have the final analysis for each event. That's what's used to do the physics, which discovers or not discovers, looks for new particles, and of course successfully found the Higgs boson. Notice these magnificent numbers. You have 350,000 cores running continuously, 2 million jobs per day. And here's 200 petabytes total, 15 petabytes each year, and so on. And it's also worth noticing that these events are partly those generated by the accelerator, which are generated at a single place, but you also have Monte Carlo data. That's data generated by the computer. The computer takes what the physicists think the event looks like, generates fake data, which would be, they think they have a model for their experimental apparatus, which is, I used to build software to actually do that. I used to do experiments in this field, and I built the software which modeled our old apparatus, which we were very proud of, but it's sort of trivial compared to today's apparatus. And you'd have this modeling software, and you generate events from a theory. You run those events through the model, and you use that to be able to decide what the probability of a certain type of event being seen, because although these experiments are very complicated, they don't actually detect everything. Sometimes events of a certain type may be very difficult to see. So in order to interpret what you see, you need to do Monte Carlo. And those Monte Carlo simulations are about half the data. And now we move on to the next section of the discussion, part D of this unit, which will discuss the actual patterns that we derive from these explicit use cases which you've gone through. Notice we have 51 use cases. We did not go through all of them. We just went through a sample, focusing on 2 big classes: streaming / Internet of Things, and images. Those are not necessarily the most important. In fact, they don't. We did not cover web search, although you could say web search is really an example of streaming. I just didn't choose that in the streaming case. Remember, I did almost all the images and all the Internet of Things examples, but only a small sample of streaming because so many of the applications were streaming. So now we'll try to draw some deductions from what we saw here, and that's going to be these ogres, which are the patterns of big data. Thank you very much.